Hey guys, this is Mr. Wing, just here to give you a prologue podcast to help you with your studies. Let's get going. Observation. If you can see it, smell it, taste it, touch it, or hear it, basically, if you're going to use a combination of your senses, it's going to be an observation. This is basically the way that we interact with the environment in which we take in information. Sometimes we're going to need the help of an instrument, which is going to help our observations be a little bit more accurate. Sometimes our observations are really small, sometimes they're really big, sometimes they might be far away. We're going to need the help of a piece of equipment. Instruments help our observations. Once we get an observation, once we take in our information, then we can formulate a conclusion. That's called an inference. Sometimes we need to make an inference about the future, like a weather forecast. That's called a prediction. Now, there's two different types of predictions. We have our cyclic, like our cyclic relationship, that happens over and over and over again. Okay, what happens here, it's really easy to predict, like the phase of the moon, sunrise, sunset, our tides. Or we can have a non-cyclic prediction, which is something that's a little bit more random, much more difficult to predict, like an earthquake or a tornado. Once we gather our information, we need to organize it. That's where we make what's called a classification system. We classify things based upon observable characteristics or properties. One thing in science, you need to make a lot of measurements. Chances are, at some point throughout the year, you're going to have to measure some time, some length, some mass, or even some volume. Okay? Chances are you're going to get a number, you're going to have to attach a unit to it. That's what we call a measurement. Chances are your teacher's going to tell you need to round to the tenths place. That's going to be one space after the decimal. Now we have two different types of units. We have a basic unit, which is a single unit, or we have a derived unit, like our density unit, like grams per cubic centimeter. That's going to be a combination of more than one. The first formula you did, percent deviation. Sometimes your teacher might have called it percent error. Basically, in science, you're going to make some calculations. You're going to mess up. We want to figure out how much you messed up. You're going to use that formula that just popped up to figure out how much you messed up. Now, in order to do the calculation properly, you need to figure out the difference between an accepted value and a measured value. And I provided a list here of maybe some synonyms that might fall into those categories. Please, when you divide a fraction, the top number goes in first, the bottom number goes in second in relation to the calculator. Just a quick example, just in case you forgot how to do percent deviation. There's my substituted values and my final answer. Notice, went to the tenths with a unit. You should too. A lot of times in science, you're going to need to see what your data looks like. That's where graphs come into play. Horizontal axis is your x-axis. That's going to be your independent variable. The vertical axis, that's your y-axis. That's your dependent variable. Together, they give us our four basic line graphs: direct, indirect, static, and cyclic. There's an example of a cyclic relationship. Notice the repeating pattern. Here's your static relationship. Notice how horizontal your line is. There's your indirect relationship. And there's your direct relationship. Okay, make sure you know how to read each type of graph. Now, before we get into density, we got to figure out how to use volume. And the most common way you're going to figure out volume is by length times width times height. But that's only going to be for a regular-sided object. Sometimes you might have irregular-shaped objects, like a rock. You're going to need to use the water displacement method. So here we go. Here I have a rectangular box. So I need to figure out what the length is going to be. My length there is going to be 6 centimeters. Okay, I need to figure out the width of my box. The width of my box is going to be 2 centimeters. Okay, and then I finally need to figure out the height of my box. The height of my box here is going to be 4 centimeters. I take those numbers. I'm going to multiply them together. Don't add them, multiply them. Okay, you're going to end up at 48.0 cubic centimeters in this example. Okay, remember, you don't always have to use cubic centimeters. You can also use milliliters as well. They're one and the same. Use the one that you feel most comfortable with. If you have an irregular shaped object, you need to use water displacement. In this example, my graduate cylinder on the left filled up to 200 milliliters. I drop my pebble in, goes up to about 270 milliliters. What you do, you subtract the two volumes. The difference tells you the volume of the object, in this case, 70 milliliters. Finally, we get into density. Obviously, density is going to be the amount of junk crammed into a specific object. There's your formula, front page of your reference table. Never have to worry about forgetting it. In this example here, you have a couple golf balls. Left-hand box, 1 golf ball. Right-hand box, 20 golf balls. One on the right-hand side, much more densely packed because there's a lot more stuff crammed into it. Just some words that you should need to know. High density, increased density, more dense, they all mean the same thing. Things are going to sink, means that they're heavy. Low density, decreased density, less dense, those things are going to float, means that they're kind of light. Now, one of the big relationships is knowing that size and shape have no impact on density of the same substance. You could have a piece of aluminum, break it up into a bunch of different pieces in different shapes. What's going to happen is, because it's all aluminum, they're all going to have the same density. Pile of rocks all have the same density. All those aluminum fittings all have the same density. And again, that relationship, size and shape compared to density, static relationship. Definitely know the difference between mass and weight. Mass is the amount of material crammed into an object. Weight is when gravity pulls on the mass. Okay, mass is not really going to change that much. Weight will when you go from planet to planet. DMV triangle, definitely need to know it. Definitely need to know how to manipulate it. Density equals mass over volume. Volume equals mass over density. Mass equals density times volume. Real quick, temperature and pressure, they're going to impact density. They're going to have a little bit of an influence in terms of how density is going to be. Again, just some words. Decrease, fall, drop, all mean the same thing. Increase, rise, stuff goes up, all mean the same thing as well. So definitely know some of the synonyms in relation to some of these relationships. Okay, big thing about temperature. Things heat up, they're going to expand. Molecules move further apart, your density is going to drop, that stuff is going to rise. The exact opposite happens when things get cool. They contract. Those molecules get really close together. Density is going to go up, and what's going to happen there is things tend to sink. We're looking at an indirect relationship here. As temperature goes up, density goes down. Indirect relationship. Warm air rises because it's less dense. Example that would be a good example of that would be a hot air balloon. Okay, cool air sinks because it's more dense. They're the exact opposite. And like I said, it's going to be indirect. So just a quick example of my balloon. What's going to happen here is my balloon is going to expand. And as my balloon expands, what's going to happen there is my density is going to drop. That balloon is going to rise up even further up. And the same concept is going to hold true for a hot air balloon. There's my indirect relationship. Okay, real quick in terms of phases of matter. Most objects on the planet, solid's most dense, then liquid, then your gas. Water's your big exception for 2 reasons. Water expands when it freezes. Most stuff expands when it's heated. And also, water is most dense in its liquid phase, then it's solid, then it's gas, from most dense to least dense. Also, water is most dense at 4 degrees Celsius, and the density of liquid water at that temperature is about 1 gram per cubic centimeter or 1 gram per milliliter. Okay, objects that are less dense, they're going to float. Objects that are more dense are going to sink in relation to the water. Okay, just some pictures of what water looks like in its gas phase, what water looks like at 4 degrees Celsius, its most dense phase, and what it looks like in its solid phase. Ice, as we know, is going to float. So if we drop a couple objects into water, that's going to be the least dense. There's my ice cube. That object actually has the same density as the water, and that object's going to be most dense because it's sunk all the way to the bottom. Pressure. Okay, when it's under little pressure, okay, it's not going to keep those molecules together. That air mass is going to expand. As it gets further and further and further apart, that density is going to decrease quite a bit. What's going to happen is things are going to rise up. The exact opposite holds true when there's a lot of pressure. Great pressure, like a garbage compactor, is going to contract. It's going to squeeze those molecules really close together. What's going to happen is your density is going to go up tremendously. And what's going to happen there? Things are going to sink. So as pressure goes up, your density goes up. Okay? And what we're looking at there is a direct relationship between the two of them. So if you look here, your molecules close to the surface are close together. High density air, as you get further up in the atmosphere, your air mass is further apart, your molecules are further apart. Low density air at the top of that picture. And there we go, my direct relationship.